All right, so yesterday we were talking about velocity and the difference between position and velocity. And so we'll talk now about, we're going to talk a little bit about acceleration and the relation between position, velocity, and acceleration, which are known as the kinematic equations. And this will tell us things like how far a cannonball goes when you fire it at a certain angle. Okay, that's the end, that's what we're trying to get to. Or even in lab last week, you dropped a ball from a certain height and it fell, and you related the height to the time. We'll get that equation. And so that's what we're aiming for. So what was our definition of velocity? You remember? How was it related to position, to a changing position vector?
It's divided by
R.
oh, that's right.
That's right. So the velocity of an object is equal to the change in position vector, which would be like the final position minus the initial position, over the time it took to do that change. I might put a delta t here for the change in time, but t would be fine as well. I'm going to write that as delta r over delta t. This delta usually stands for change. So this would be the change in position over the time it took to change. R final is the final position. R is the RI initial position of an object. And that's what we covered last time. Okay? The magnitude of the velocity vector has a special name for it. It's called the speed of the object. So when we talk about speed, we mean magnitude of velocity vector. Well, velocity vectors themselves can change. So for instance, say I have a car drawn as a box, and say that at time t equals 0, the velocity vector is small. And then let's say that some time later, maybe I'll write this as t final. It's changed its velocity. It has a much bigger vector. Why don't I write this as v initial? Clearly in that time, if it starts out slow and then speeds up, the velocity vector has changed. And there's a relation that's looks a lot like the relation between position and velocity. There's something called acceleration that looks a lot like, that's related to velocity in much the same way as position is related to velocity. So I'm going to define something called acceleration. That's a vector that's equal to the final velocity minus the initial velocity of an object divided by the time it took to go from final to initial. Or maybe I'll leave that as a delta t, the change in time it took. And this is a definition. This will be our working definition for the acceleration of an object. Okay. So for example, let's say that you have a Bugatti Veyron. Which is an old hypercar, but it's a good one. And that thing could go from 0 to 60 miles per hour in 2.4 seconds. By the way, that thing has the second highest top speed of any production car. Anyone know what the first highest, which one has the highest top speed?
Wasn't it a Lamborghini?
No, No, it's the Hennessy Venom, which is a Lotus, extended Lotus. And that's anyway, so just for your edification about cars. But the Bugatti Veyron's pretty close. Top speeds, well, I think the S, it's like 270 miles an hour. Something like that. Anyway, let's see if we can figure out what the acceleration is as it's doing this. So as it's going from 0 to 60, let's draw a little picture. Everything here would be in one direction. X direction, we're just going to say, goes that way. So everything, all the velocities are going to be in the X direction. The initial velocity would be 0, and then the final velocity at some later time would be 60 miles per hour. Let's see if you can write that in meters per second. So 60 miles per hour. How do we go from miles per hour to meters per second? Remember?
16.8 or something, 0.3 meters.
Wow, you got it. 16 point, okay, so 1 mile. So let's just do this, 60 miles per hour times, I'm going to multiply this by 1 until I get down to meters and over second. So 1609, we discovered this. I think it's 0.3 meters. It's the same thing as 1 mile. And then how many seconds are in a mile? Or how many seconds are in an hour?
3,600. 1 hour, 36
1 hour, 3,600 seconds. So if I do this multiplication, miles cancels, hours cancel, meters don't cancel, hours cancel, and I'm left with meters over second as the units. So if I do this multiplication, 60 times 1609.3 divided by 3,600, what do I get?
26.8.
What was it?
26.8.
So 26.8 meters per second. Okay. So, for this Bugatti Veyron starting out at rest and going faster, the initial velocity is 0 meters per second, and it's a vector, but 0 is 0. I don't have to put the unit vector on there, but I will just for the heck of it. The final velocity, that'll be 26.8 meters per second x-hat. X-hat means it's in the x direction, right? And so the acceleration would be v final minus v initial divided by the time it took, which would be 2.4 seconds. So if I plug that in, I would get 26.8 meters per second divided by 24, or 2.4 seconds x-hat. And what do you get when you do this?
11.2.
Is 11.2. What would the units be?
Meters.
So meters per second
Oh.
divided by another second.
Meters per second squared.
Well, it's
No.
meters per second squared. So I have a meter divided by a second divided by another second.
Yeah, that's what I said.
Oh, okay.
Yeah.
X-hat. And so that's the acceleration of the Bugatti Veyron. The magnitude of this acceleration is 11.2 meters per second squared. And that's a fairly good acceleration. Although you can probably, I don't know how much those things cost anymore. They don't make them anymore, so they're a little bit old. But they were about $2.5 million to $3 million. You can probably buy a $50,000 sport bike that would do the same thing. Probably even $25,000. So, of course, the top speed would be a lot lower.
Get them in 60 for a quarter mile.
Yeah. All right. That makes sense about how to calculate that acceleration. Let's do another example. By the way, I want to point out the units of that right are meters per second squared. So it's in acceleration. And you're in SI units, that should be the units. Okay, so this one's a little bit different. Let's imagine that you have a street like this, and you have a car traveling this way at 10 meters per second, and then it takes a left hand or a right turn, and then it's traveling this way at 10 meters per second at a time of 2 seconds later. What would be the acceleration during the turn? So in this case, the speed, magnitude of the velocity doesn't change. At least what we know, it's 10 meters per second here, and it's 10 meters per second there. But the velocity vector is changing.
Setting a 90-degree angle.
Yep.
You notice that you're starting from 0 to 40 in 10 seconds, 2 seconds, 10 minutes, 2 seconds.
Well, I don't know if we're going from 0. We're going to write the velocity vector here. We're going to write the velocity vector here. We're just going to subtract the 2. And then divide that by the 2 seconds. Yeah. And so this may be a little bit unrealistic, actually, but we'll do it. Let's introduce a coordinate system. So upwards we'll call y as it's drawn, and over we'll call x. So what's the initial velocity vector? 10 meters per second in the y direction, right? So that'd be 10 meters per second. All of that's in the y direction. If I drew it, I'm trying to draw this so that the y aligns with this initial velocity. What's the final velocity?
10 meters per second.
There's like an X to it.
That's right, 10 meters per second in the x direction. Okay, so if I were to write my definition for acceleration, it would be the final velocity minus the initial velocity divided by the time it took, which was 2 seconds. That would be 10 meters per second x hat minus 10 meters per second y hat over 2 seconds, which would be 5 meters per second squared x hat minus 5 meters per second squared y hat. So if I were to draw on an xy coordinate system the acceleration vector, it would point in the x direction and it would point in the negative y direction. So the acceleration would look something like this. This length being 5 meters per second squared, and this length being 5 meters per second squared. You follow? All right, so the component of the acceleration in the x direction is 5 meters per second squared. The component of acceleration in the y direction is 5 meters per second squared with a negative sign. Okay? You guys good with that? All right. We'll do a little bit more relation between acceleration and velocity.
So then could we go in and do like to find the one?
What's that?
Then could we go in and do like a squared plus b squared plus c squared to figure out what the
Magnitude.
magnitude is?
Okay, we can do the magnitude of the acceleration. Magnitude of the acceleration would be exactly that. It would be 5 meters per second squared plus 5 meters per second squared. And that would be square root of 2 times 25, 50 meters per second squared. And that'd be somewhere a little over 7, right?
Yeah, 5 square root 2.
But the two different sets in for A, that's acceptable for an answer, right? You don't-
This is the acceleration. If I asked for
Oh.
if I asked for the acceleration, this was the answer.
Okay.
If you wrote this, that wouldn't be correct. That's the magnitude of the acceleration. Okay? So magnitude, size of acceleration. Acceleration, velocity, like position, they're all vectors. And so you need x and y components, or x, y, and z components, or whatever it is. Yeah.
What about the, like, A is X and A is Y over there?
These are the components of the acceleration. This would be the acceleration in the x direction, 5 meters per second squared. Acceleration in the y direction, negative 5 meters per second squared. It's negative because it accelerates in the negative y direction.
Could we write it either way, or you want that one?
This is the correct form for writing the vector. If you wrote out both of these components, that's the same information there, okay? So that would probably be fine.
Stand that out, our y is going to continue to go down.
Well, yeah,
Over time.
if you kept on accelerating this way, keep on moving, you'd be moving differently.
But in your example, aren't we going straight east, straight x direction or whatever? We're
Yeah.
no longer accelerating in a y direction.
Yep. We're talking about the average acceleration between this point and this point.
Train
Yeah.
time is going to go.
Yeah. Once you're here, if you looked at it later, it was 10 meters per second, but still going this way between here and here, no acceleration because the velocity is the same. Okay. So the v final minus v initial would be 0. All right, are you guys? Does this make sense to you guys? All right, we're gonna do one quick thing, and then I'll ask you if you have any questions on homework. What I'd like to do is to come up with a set of equations we'll be using from here on out, called the kinematic equations. And this relates acceleration, velocity, and position. And it's fairly easy to, well, I won't say it's easy, but it's not horrible to come up with them. Even at the algebra-based level, at the calculus-based level, it's even easier, but we won't do that. So, let's say I have an acceleration, which I can write as ax, x hat, plus ay, y hat. I know that this is the same thing as the final velocity minus the initial velocity divided by the time it takes to go between those velocities. And so I'm going to write that as ax, x hat, plus ay, y hat. These velocities can have x and y components, so I'm going to write this out in gory detail. So I'm going to do v final x, x hat, plus v final y, y hat. This is the final velocity vector written out with components, final x and the y, minus the initial x, x hat, minus the initial y, y hat. So this is minus the initial velocity vector. Put minus signs on both those components. All divided by the time. And that's going to be equal to this acceleration in the x direction plus the acceleration in the y direction. All right, I'm going to group whatever is proportional to x here. And that has to be whatever equal to whatever is proportional to x hat here. Whatever is proportional in the y direction over here on this side is going to be, of the equation, has to be whatever is proportional to y hat on this other side of the equation. So if I look at that carefully, I'll see that the final velocity in the x direction minus the initial velocity in the x direction divided by time is going to be the acceleration in the x direction. Do you guys follow that?
Yeah.
V final x minus v initial x, that's what's in the x hat direction, divided by time. That has to equal whatever's in the x hat direction over here, in case of x. Same thing in the y. Just change the components, when we leave from x to y. So these are my accelerations in the components of acceleration in the x and y direction, written in terms of the velocities in the x and y directions. Let's look at this, and let's go ahead and solve that for the v final. So this would mean that if I multiply both sides by t, I get that the final velocity in the x direction minus the initial velocity in the x direction is the acceleration in the x direction times time. Or final velocity in the x direction is the initial velocity in the x direction plus the acceleration times time. If I were to plot velocity in the x direction, the final velocity in the x direction versus time, this would look like a straight line with the slope being the acceleration. See, this would be like y equals mx plus b. So if I would look like it would start out at the initial in the x direction, slope up, and then the slope would be acceleration in the x direction. Just so you have a sense of what's going on. During this time, this thing's kind of traveling at an average velocity. Okay, it's not traveling at this velocity or this velocity, it's traveling at an average velocity. Which would be halfway in between. I'm going to write this as V average. This average velocity in the x direction, I can write it as the final velocity in the x direction plus the initial velocity in the x direction. If I average two numbers, right, I add them together and then divide it by 2. Now, let's go back to our, we're gonna save this just for a second, okay? And we're gonna go back to our position, relation between position and velocity. Now remember, velocity is the final position of an object minus the initial position of the object divided by the time it took to go from the final to the initial position. If I were to write this out in components, I would see that the velocity in the x direction would be the x position of the position minus the initial x position divided by the time it took. We can see that if I'm moving at a constant velocity, that the final x position would be equal to the initial x position plus the velocity in the x direction times time. This is good if this is a constant velocity. Again, if I were to draw the position as a function of time, you get a straight line, with the slope now being the velocity. Anyway, I won't worry about that too much.
Is there a reason you're using the vertical as X and the horizontal as Y, or is that just?
Yeah,
Does
it's
that have any-
confusing. I'm using the vertical as the X and the horizontal as the T.
Oh, okay.
And it's, I don't mean to confuse you.
Oh, no, it's fine.
It's just graphing the X velocity as a function of time.
I didn't, just wondered if that was like a standard thing. They always put X vertical and.
Usually, if I have X and Y, it's usually Y is vertical, X is horizontal.
Yeah.
If I'm graphing them as functions of time, usually the times
The time is
the
horizontal.
horizontal.
Fair enough.
Okay, so this is my relation between the position and velocity. Now, what I really should have there is the average velocity while it's traveling. Okay? If it's not traveling with a constant velocity, then what I need is an average velocity in this in here to get the final position and the initial position. How the final position is related to the initial position. And so what I would do is I'd write this as B average X. And I'd take this and I'm going to plug it into here. So I'd get that the final X position is equal to the initial X position plus the final velocity plus the initial velocity divided by 2 times the time. Now, I'm going to go way over here and I'm going to sit, and I know how the final velocity is related to the initial velocity. So I'm going to take this, go way back over here and put it in for the final velocity. So I guess I had X, final X before. So that's going to be, this is the initial velocity plus the acceleration times the time. So going way up here, and this is, I know, a little bit tricky. I'm going to get that the final X position is equal to the initial X position plus initial X velocity plus the acceleration in the X direction times time plus the initial X, or plus the initial X, this should be an X here, velocity over 2 times T. There's 2 velocity initials in the X direction here. So I could write this as X initial plus 2 velocity in the initial in the X direction times time, because all of these are multiplied by time.
What about
Two.
AX?
Plus, yep, exactly, AX t squared, whole thing divided by 2. I can get rid of that 2. I could write this as over 2 here plus over 2 here. And I could get that the final result, and this is just what I was trying to derive. It's not as important on how we got there as what this answer is going to be. That the final x position is going to be the initial x position plus initial velocity in the x direction times time plus 1/2 the acceleration in the x direction and the square of the time.
Where did the square for the t come from on the second one there?
See, my final x velocity was initial x velocity plus acceleration times time.
Okay.
And I have to multiply all of this by time, so it became a t squared
Oh,
there.
okay, sure.
All right. This here is called kinematic equation. This will be, just using this equation will be what we'll end up, well, for the rest of the week, and we'll do it all throughout the class. All right, this relates position, final position, and initial position to acceleration, velocity, and time. Now, it's standard to start the initial time, to call the initial time t equals 0. Okay? And then the final time, the final position, I could write x at any time. So this would be x at time t. That's the final time we're interested in. I could write it at 0 time, plus the initial velocity in the x. It's more standard to write it as v naught x if the initial time is 0. T plus 1/2 a acceleration in the x direction times t squared. And then this actually can often gets written x naught as the position at time 0. Okay, same thing as right up here. What we called x and what we called y, there was no real reason. You know, all of this stuff, we just looked at the x direction here. I could have done the y direction too, and it would have been the same, exactly the same. Except that I'd replace the x's with the y's. So I could get a second equation, which I'll do over here, that y at any time is equal to the initial y position, y at time 0, plus the velocity in the y direction at time 0, plus 1/2 acceleration in the y direction times the square of the time. All right, this is derivation of these equations. These two equations are what we really want. The derivation is good if you follow it. If not, we probably won't use it much. But we will be using these equations. And you can see where it comes from. It's very simple. It's just that the distance traveled is basically, this would be the distance traveled, x final minus x initial. It's just velocity times time. And we just plug in an average velocity there. Okay. And the average velocity involves an acceleration. Make sense? This, by the way, assumed a constant acceleration. All right. You want to do an example? I think maybe we need to, right?
But do we have to come up, like, do we have to do what you just did?
No.
to do.
We just need these equations here.
Okay.
If you could do that, it's good, it means you understand. I'm gonna go stop this.
It should help with what.
Yeah, but